Welcome back to Programming with Python. Today we will discuss the very important concept of functions. Functions are very useful in programming because they allow us to structure our code into independent blocks that act as black boxes. So the idea is that we structure our code into blocks whose interior we don't really need to understand. We just need to know how to call the function in order to make use of it. Also, functions allow us to avoid repetitions and thereby reduce the complexity of our code and make it much more readable. We will use functions extensively in the lab tests and also in the final coursework, so let's make sure that we understand very well how to use them. Again, I will use an example to motivate the use of a function, and the example that I listed here is something that you have already seen in week 1. This refers to the problem of computing the nth Fibonacci number using integer addition. Let's quickly discuss this code here. Let's say we want to compute the nth Fibonacci number. We'll first ask for an input from the user to define the integer n, and then we can do it in the following way. We define an integer variable f0 and another integer variable f1 as integer values 0 and 1 respectively. It is advisable not to think of these variables as the 0th and first Fibonacci number, but as a Fibonacci number, f0, and its successor, right? So 2 consecutive Fibonacci numbers. Then we have a while loop here, and as long as n is strictly greater than 1, what we'll do is we compute the next Fibonacci number, nxt, as the sum of the previous 2. This is exactly the Fibonacci recursion. Now, you might wonder why I call the variable nxt and not next. The reason is that next is a reserved keyword in Python, so we cannot really use it as a variable name. Once I've computed the next Fibonacci number, I can forget f0 because this was too far in the past. I can overwrite it with the Fibonacci number f1 that we had previously. I have now remembered f1 in the variable f0, so I can overwrite f1 with the next Fibonacci number that we have already computed. Now, this while loop would not stop if I were not to increase or decrease the index of n. In this case, of course, I want to decrease n by 1, and then I would continue here as long as n is greater than 1. Once this while loop is completed, I want to print out the result to the console. So, for example, with an input of 7, this piece of code would return the 7th Fibonacci number, which happens to be 13. Now, when dealing with while loop, sometimes it is advisable to think about edge cases in order to make sure that we are computing the nth Fibonacci number and not the Fibonacci number of index, let's say n-1 or +1 by accident. So let's inspect this code for the case that n is equal to 1. Let's say I want to compute the first Fibonacci number. Would this actually work? Well, if n is 1, we still define f0 and f1 as given here, but then we will actually not execute this while loop, right? Because 1 is not strictly greater than 1, so this condition is false, and the body of the while loop will not be executed. Therefore, for n equal 1, we will immediately jump to this print command here, and luckily I have actually defined f1 above here. So for n equal 1, I will just output the first Fibonacci number, which happens to be 1, so everything is fine. Okay, let's try n equal 2. So let's say n takes the value 2 here. I will define f0 and f1. Now 2 is strictly greater than 1, therefore this while loop will be executed. And what I do is I compute the next Fibonacci number as the sum of the previous 2, so 0 plus 1 is 1. nxt will now take the value of 1. I will define f0, f1, decrease n by 1, and then go back up here. Now I have decreased n by 1, therefore this condition is no longer true. The while loop will end. Okay. So you can easily convince yourself that for the case that n is equal to 2, I will compute f1 as the sum of the first 2 Fibonacci numbers, which happens to be 1. Right? So the second Fibonacci number is also 1, like the first, and this program would actually compute this accurately. So everything is fine. When you deal with while loops, I always recommend trying out a few cases, in particular the edge cases, so very small integers or very large integers, depending on the problem, in order to make sure that your code produces the exact answer that you really want. Now, all that we have to do in order to transform this piece of code into a function is to basically take the code as it is and put it inside the body of a function definition. So this is how a function definition in Python looks like. It starts with the keyword def, which indicates to Python that we are now defining a function. Then this is followed by a name. So a function name, like variable names, should be descriptive, right? We are computing here a Fibonacci number, so let's call our function Fibonacci. Then the name of the function is followed by a list of parameters in brackets. Okay, so opening brackets, and then we need to identify the input parameters for our function. Now you can think of a function similarly to what we have discussed for algorithms at the beginning of the course. Remember, algorithms, they take some input data, they do some transformation on this data, and they return the data or output the data back to the user. Functions can be thought of in the similar way. We need some input data, we do some computations, and then we return what we have computed. So what do I need for this function? Well, if you're writing a function to compute the nth Fibonacci number, then you need to specify at least what n is, right? Now we will actually not specify n, we will only declare that this function accepts an input parameter which is n. Okay, and that's what we're doing here. Then this is followed by something that is called a docstring. Docstrings are defined by using these triple quotation marks. Note that the docstring has to be indented. Everything inside the function is indented to the same level. And here we basically just explain what this function is doing in human readable text. So our function will take one input argument n, and it will return the nth Fibonacci number. That's really what our function is supposed to do. Now, what you have here is exactly the code from above. It's computing the nth Fibonacci number. But note that we are not asking for an input for n here, because what will happen is that the value of n for which we want to compute is provided to the function from the outside. And this is extremely important. There is no input command inside our function, and there should never be any input commands inside your function, because the parameters are provided from the outside to that function. We will see in a second how to actually provide parameters to this function. So we have computed the nth Fibonacci number, so we then want to output it. And the way this is done in functions is with the return command. Okay, so return f1, because f1 will contain the nth Fibonacci number after this computation here is completed. So just to summarize, def keyword, descriptable function name, for example Fibonacci, brackets with a list of input parameters, in this case there's only n, followed by a colon. Then we have an indented block defining the function, starting with a docstring, so that's a description of what the function is doing and the number of input parameters it requires and the types of input parameters. Then the computation, and finally the return keyword, which returns the value that we have computed, which in this case is f1. So let's go to Spider and see what this actually does. I will copy and paste the code that we have just seen into my editor, and I will execute it. Execute in a dedicated console, remove all variables before execution. As usual, I'm selecting these for convenience. Run. Connecting to the kernel usually takes a few seconds, so we are waiting for that. And execution is completed, and we see that basically nothing appears to be happening, right? So we don't see any output, nothing going on here in the console. So what has happened? Well, actually a lot of things have happened. As we have executed this code, Python has defined a function called Fibonacci, but it has not actually executed it, right? So there's a difference between defining a function and actually using it. So if I want to now make use of this function, I have to call it. And the way we call functions in Python is by typing their name, Fibonacci, followed by a bracket, and now I need to provide an input parameter for n. So let's say I want to compute the 7th Fibonacci number. I can just type Fibonacci 7 and hit enter, and what this function does is it will do the computation just as we have seen before, using for n the value that I have provided in my function call. So n is 7 in this case, so it will compute 13, which happens to be the seventh Fibonacci number. And once it's done with that, it will return this value. And when the return keyword is executed in Python, the value is basically returned by that function. If I want, I can define that as a variable. So I can type call Fibonacci with the input parameter 7 and assign the returned value to a variable, let's say x. Now I have x available. And of course, again, it's 13. And here you see a big benefit. I can now compute any Fibonacci number I want by calling this function with different input parameters. So let's say I want to compute the Fibonacci number with index 13. Well, then I call Fibonacci of 13 and it will return 233. Right? So if you are in the situation that you need to compute multiple Fibonacci numbers, then why not define it as a function and make repeated use of it? Now I would like to highlight that the return statement in the function is providing us with the computed value, but it also does something else. It actually interrupts the execution of the function. So as soon as Python encounters the return keyword in the function, that function will be interrupted. Okay. And it also provides, as mentioned before, the return value. I have already discussed briefly how to call a function, so we'll just call a function by its name, and we need to provide the input parameter n in order to do so. If you call a function without its input parameter, so if you just type Fibonacci, something different will happen. Python will just tell you that essentially this function Fibonacci has been defined in memory, but it will not actually execute it. Likewise, if you call this Fibonacci function with an empty parameter list, you will get an error because we are really required to provide one parameter, and Python tells us that Fibonacci is missing one positional argument, which is n in this case. Right? So we really can only call this function with one input parameter corresponding to the value of n. Otherwise, we get an error message. Right. It is also perfectly fine to call Fibonacci with some more complicated expressions for the input. So let's say I'm calling Fibonacci 6 plus 4. What will happen here? Well, again, Python interprets this expression from the inside to the outside. So when it sees Fibonacci 6 plus 4, it will first evaluate this expression here. 6 plus 4, well, that equals 10. Okay, I need to call Fibonacci of 10, and Fibonacci of 10 happens to be 55. So let's discuss the role of the input parameter n. It turns out that input parameters are usually copies, or the parameters of functions are usually copies of the input arguments. I have an example here that I will come back to in a second, but let's first look at our Fibonacci code. So recall that we have our function still in Spyder, here it is, and let's say I define a variable n to take the value 5, and I then call the Fibonacci code. So let's say I want to call this, and I will output the returned value using the print function. So I do print Fibonacci of n. We run this, and what we see here is 5 being printed out on the console. Indeed, the fifth Fibonacci number happens to be 5. When I call this function, the value of n, which is 5, has been handed over to our Fibonacci definition. And then we have run this loop here. And you will notice that inside our loop, I have decreased n by 1 at each iteration. So one might be tempted to think that after this function has completed and returned its value, the value of n that I defined here has changed. So let's see if this is actually the case. So I'm gonna print out n as follows and rerun my code. And you see n is still 5 even after this Fibonacci function has been called. What really happened here is that the variable n that I have here is in a different scope to the variable n that I have here. Okay, so this is what I mean by arguments being copies of the input parameters. When you hand over the value of n to your function, then this n that we have here is actually a different n. It's a copy of it. So when we change it at each iteration, we do not really affect the variable n that I'm defining outside my function. And that's very important. This means that functions behave like black boxes, right? They get their input parameters, they do their computations, but they do not mess with any of the variables that you have outside, right? So, and that's of course quite desirable property, right? Because you just want to be able to define your function and call it without caring too much about what is going on inside that function. And this black box behavior actually makes sure that you can treat functions in that way. Here's another example that demonstrates the black box behavior of functions and the fact that we are working with copies of the arguments. It's a function called inc, which stands for increment, let's say, that takes two input parameters, x and y. So here's an example where you have two input parameters, and as you can see, they are simply separated by commas. Function takes the value of x and increments it by the value of y, and then just returns the variable x. Now I call this function with two input parameters. The first one is a variable called a, which initially has the value 17. And the second parameter will simply be 2, and I assign the returned value to the variable b here. We then print out both of these variables, and as you can see, after I have called this function, the original variable 17 is still available in a. So the value of a was not changed, even though the value of x inside that function was modified. And again, this is because the function was called with a copy. So this value of a was copied into the variable x. We have modified the variable of x, but the original stays intact. Another property or consequence of this black box behavior is that local variables, so variables that belong to a function and are not visible outside of it, truly vanish when the function execution completes. Here's an example again to illustrate this. I have a function called test, which takes a single input argument defx, which I want to be a Boolean variable. If this Boolean variable has the value true, I will define a variable x with the value 17 and then print out x to the console. If I call this function with something that evaluates to false, then of course I'm skipping this definition here and I will just print out x to the console. Okay, let's call the function for the first time using true as the input parameter. If it's true, then I will define the variable x with the value 17. And indeed, as you can see here, the function prints out x has the value of 17. I then call the function again, but this time with the input parameter false. Now, because I call it with false, this definition here is skipped, and I immediately try to print out x to the console. And this fails because this variable x is not defined, so I cannot actually print out its value. Then in Python, this is called an unbound local error, and you see the description here. The local variable x has been referenced before we assigned a value to it, right? So we tried to print out the value of x before even assigning it. And this is not allowed in Python, and therefore an error occurs. And what this illustrates is that we have actually defined x when we called the function for the first time, but when I call the function again, this value of x has been forgotten. Now, just a word of caution, when it comes to more complex data structures like lists, sets, and dictionaries that we will discuss later on in the course, this idea that the input parameters for functions are copies of the arguments no longer applies. Okay, so there the situation is slightly more complicated, but we will learn about this later on in the course. It's certainly true for integers and floating point numbers that you will deal with copies of the input variables. A bit more on returning values. So there is another keyword in Python called yield that can be used instead of return. We will learn this later on. And also in Python, it is actually possible to return more than one value. Right? And this is not the case in other programming languages, but in Python it is perfectly fine to return more than one value from a function. Also, we will address this later on in the course. If you define a function that does not have the return keyword, then by default this function will return none. Remember this strange value of the none type. This is exactly the one that is returned by a function if you don't use the return keyword. You can try this out in Spyder quite easily. So if I go here, let's write a function that just does some random computation, but then does not actually return anything. So what happens when I call Fibonacci of 7 and I print out the returned value? It's none. Okay, so this is this mysterious data type none. Okay, a function can also have more than one return statement. It is very important to understand that as soon as the return keyword is encountered by Python, it will stop the execution of the function and return to the outside scope, so the scope from which this function was called. And this can actually be used in a meaningful way in order to structure our code without using too many if and else statements. Here's an example to illustrate this. Let's say I want to write a function max1 that takes two comparable input parameters x and y and returns the larger of the two. Okay, now I can do this using an if-else block. I can ask, is x greater than y? Using this if statement here. If this is the case, I want to just return x because x will be the larger value. And as soon as this return is being found by Python during the execution of the function, this function will end. Okay, so the else is not even looked at by Python. If this condition is false, I will execute the else block here and I will return the value of y. So that's one valid way of implementing this max1 function. A completely equivalent way is to do the following in the function called max2. If x is greater than y, I will return x because clearly it is the greater of the two input arguments. Otherwise, I will just do return y. Now, why is this the same? Because this return y is actually not executed when return x is being executed. So I can get rid of the else block here. Okay. So this is slightly more elegant because I'm saving this else branch here. And you can easily verify in Spyder that both of these behave in exactly the same manner. So what is the use of these long explanations, these so-called docstrings at the beginning of each function? Well, the purpose of them is to give valuable information to anyone using your function without them being required to read the code of your function. This docstring precisely defines what are the expected inputs of your function and what will be the outputs of your function. So in a sense, you can think of a function as a black box, and the only information that you need in order to use this black box should come from the docstring. Now the docstring, as we have seen before, is defined using these triple quotes. It's indented to the same level as the rest of your function code, and basically it's a human readable string. And this here is an OK docstring. It actually tells us that this function takes two comparable values x and y as arguments, and then it returns the larger of the two. Right? So using this information, I would be able to call this function. Now it is possible to read out the docstring programmatically, so you can type after you have executed this function, so it's available in memory. You can type max1 full stop and then underscore underscore doc underscore underscore. Okay. This will return a string, and this string corresponds exactly to the docstring that you have defined here. Now this is very useful because if you have a larger software project with hundreds or thousands of functions, you maintain your docstrings well, you can use this functionality to create a manual for your software product automatically from the docstring. there are several software products available. There's, for example, Sphinx, which allows you to produce a reference manual automatically from well-documented Python code. Technically, of course, docstrings are optional, so they are not necessary in order to run the code, but they should be standard part of any of your Python programs that you write. The language that is used for writing docstrings is called Markdown. It's very widely used for formatting documents. For example, these lecture notes here are actually written in Markdown, and they should be also used in docstrings. You see, for example, here that I have put the variables x and y into these quotes here. This is part of the Markdown language. If you want to learn more about Markdown, I have a few references here in the lecture notes that you can read. Now you might object that, well, I'm the only one reading my code. Why should I bother writing these docstrings? My answer is it doesn't matter. You should always write meaningful docstrings, because even the future yourself in, let's say, 2 or 3 or maybe 6 months will no longer remember what you have done today. So it's always good to write docstrings that make it easy to reuse your code. In a sense, it could be said that code without any documentation is useless code, right? Because if you think of it as a black box, if you don't give the instructions as to how to use the code, you can't really make any use of it. Sometimes it is desirable to call a function with different numbers of input arguments. We have seen a function with 1 or 2 input arguments. They can be multiple input arguments, and sometimes it's useful to have a function that accepts a wide range of different signatures, as this is called. Now, you already know one of these functions, namely the range function. Remember, the range function could be called using 3, 2, or just 1 input argument. And the question is, how do we write functions ourselves that behave in that way? Here is an example of a function called digitsum that does the following. It returns the sum of all the digits of an integer n that, when divided by another integer d, give the remainder r. So it's a function that clearly takes 3 input arguments, n, d, and r, which are specified here in the docstring, and it returns the sum of the resulting digits. It's a very simple function. It's written here in code, but this should not be of importance at the moment. What I'm interested in is the question, would it make sense to call this function with fewer than 3 input arguments? And the answer is, of course, dependent on the context. And we should discuss this maybe with an increasing number of input arguments. So the first question is, would it make any sense to call this function without any input arguments, not even the number n, whose digits we want to sum? It doesn't seem to make any sense. It's hard to imagine anything meaningful in this context of 0 input parameters. So no, at least we want 1 input parameter. Now, if I call my digitsum function with just 1 input parameter, in the most canonical case, what I would want this function to do is to compute the sum of all the digits. Now, how do I compute the sum of all the digits of n using my function definition here? If I want to compute the sum of all digits, I simply need to check whether, after being divided by d equal 1, it leaves a remainder of 0, right? Certainly every digit satisfies this property. When you divide it by 1, there's a remainder of 0. Therefore, when I call this function with just 1 input parameter n, then maybe I want the value of d to be automatically assigned to 1 and the value of r to be automatically assigned the value of 0. Okay. That's what is being discussed here. If I call this function with just 2 input parameters, n and d, so if only r is omitted, perhaps it would make sense to interpret this as calculate the sum of all digits of n that are divisible by d. Okay, so in this sense, I want r to be equal to 0. So it turns out that in both cases where we are missing input parameters, r equals 0 seems to be reasonable. Okay, and that's actually a good situation to be in, because it means we can define r to be 0 by default in any case, independent of the value of d. And as we discussed before, if d is not provided, maybe we always mean that d is equal 1 in this case. And that's what we have here. So here is the same function from above, but now I have in the header of my function definition specified that d will take the value of 1 by default if it is not provided, and r will take the value of 0 if it is not provided. So let's test out how this function can be used. I copy and paste the code, and I have omitted a docstring here just to have everything on the screen, but of course normally we should have this very long detailed docstring in our function definition. So let's execute. As you can see, nothing appears to be happening, but the reason is that we have just defined the digit sum function. We haven't really called it. So if I want to call it, I can do so on the command line, and let's try out. So what is digit sum of 1, 2, 3? Now if I call it with just one input argument, then by default d will take the value of 1 and r will take the value of 0, and therefore we will compute the sum of all digits, which after being divided by 1 leave a remainder of 0, which are all of them. So we really expect this to return 6, and indeed it does. Now if I call digit sum of, let's say, 1, 2, 3, 4, 5, 6 with one more input parameter, let's say 2, then what do we expect this to do? Well, this should compute the sum of all digits that after division by 2 leave a remainder of 0. So these are all the even numbers. So here we expect 2 plus 4 plus 6, which is 12 as an answer. And indeed, that's what we get. Now, in principle, all the parameters can be given default values. I could even give a default value to the first input parameter n in our example, if I wanted. However, there is one rule that always needs to be observed. All the parameters without the default value must appear before those that have a default value. So you can see this in our example here. N is the first input parameter, and n does not have a default value. All the ones that have a default value follow n, right? And this order is important. In other words, this example here would be invalid. It is not allowed to have a default value for the first 2 input parameters, let's say n and d, and then no default value for the final one, which is r. The reason is very simple. It would not make any sense to call this function now with 2 input parameters, right? If I call digit sum 5, 1, what would this mean for r? R doesn't have a default value in this case, so it is unclear that the value 5 should be assigned to n or d. If you had more input parameters, there would be even more confusion. So this single rule here needs to be always observed. If you call a function like digit sum that has a few of its parameters not having assigned any default values, then it is of course not possible to call it without any input parameters. So if you just call digit sum with an empty parameter list, this would cause an error. Another thing that is very specific to Python are so-called named arguments. This means that when we call a function, we can also specify the name of an input parameter. Here's an example. I have a function called pfv, which simply stands for print 5 values, which takes 5 input arguments a, b, c, d, and e, of which c, d, and e have some default values 3, 4, 5. Right? And all this function does is it just prints out a, b, c, d, and e to the console. Now all of these calls here are valid. I can call it with 5 input arguments, in which case I will just print out the corresponding values, right? As you can see here. I can call it with just 4 input arguments, in which case e will be assigned the default value defined here. And you see that I'm printing out 17, 19, 23, 29, and 5 has been defined up here in the header of the function definition. And likewise, you can call it with just 3 or 2 input arguments. However, because C, D, and E all have default values, it is kind of annoying to have to specify C and D only to specify E. Right? If I just want to change the value of E and keep C and D as they are, namely 3 and 4, it would be useful to have a way to just specify the final parameter E. And in Python that's possible. You can call PFV in the following way. You have to specify A and B for sure, because they don't have default values. But then you can type E equals 31. Okay. So what this does is it will now know that what you're defining here should really be assigned to the variable E. And you can still use the default values of C and D. So in a sense, you can skip these default values by providing the name of the variable that you want to overwrite. It is even possible to insist that you call your function with named parameters. And that's done in Python using this star operator here. So this function definition here will now mean that you can call your function with 3 input parameters, just providing numbers. But as soon as you want to specify D or E, you need to do this with the named usage. So for example, it would not be allowed to call 17, 19, 23, 31 here, because D now, or E, whatever you want to specify, needs to be called as a named parameter. Okay, so for example, this would be valid. You can call that function with input parameters 17, 19, 23 and the value of 31 for the variable D. Function calls can also be used as conditions, and there is something called lazy evaluation that we need to learn about. Let's have a look at this piece of code here. I'm defining a function f, which takes a simple input argument x and just prints the value to the console and then returns the value. Note that it's a different thing to print something to the console or to return a value. If you return it, you can actually do follow-up computations with this value outside your function. Whereas if you just print something to the console, you can't really make use of it within your program. Now, what will the following code here print? What I'm doing is I call f with input parameter false and f with input parameter true. So that's an AND statement here, right? Remember, AND statements are true if and only if both of the components evaluate to the Boolean value true. In the first instance, this here will call my function f. It will print out false to the console, you can see this here, and return the value false back to my main program. So this expression here will evaluate to false. It seems that then immediately Python decides to jump to this else block here, the cake is a lie. And this makes sense, right? If this expression here is already false, then everything that is concatenated using an AND statement cannot be true. Therefore, Python goes the lazy route and decides, well, I'm just jumping here immediately. So in other words, because this here evaluates to false, this call is never actually executed. F_true is never executed, you see, because true is not printed out to the console using this program. This is called lazy evaluation, and it can be used in several circumstances. So let's look at an example where lazy evaluation is indeed very useful. Here is a short piece of code that takes two input parameters a and b, and it then simply checks whether a is divisible by b, and it prints out the according message to the console. I'm going to copy and paste this to Spider, and then we'll discuss it. And instead of using inputs, I will use fixed values here. Okay, so let's say a is 12 and b takes the value of 4, and execute. And indeed, the code prints out that 12 is divisible by 4, which is certainly true. If I change b to 5, then it will print out that 12 is not divisible by 5. Now, let's try this with a value of b being 0. It will print out 12 is not divisible by 0, and that's exactly what we want to see here. However, we have actually used lazy evaluation without noticing it. If you look at this if statement here, what we do is we first evaluate or check if b is non-zero, and then we check if a is divisible by b. Right? These are two conditions. Now it turns out if you were to check that a is divisible by b, if b is 0, then of course you have a division by 0 and this would result in an error. Right? So the circumstance or the fact that we have checked whether b is non-zero first has prevented us from encountering a division by 0 in the second statement here. In other words, if I swap the order of these two statements, if I first check if a is divisible by b and then I check whether or not b is non-zero, then this same example would lead to a 0 division error. So this lazy evaluation can come in very handy. Obviously, if we know that b is 0, we don't actually need to check whether a is divisible by b or not. I have used the term scope previously in this lecture when I explained how the input arguments of functions are copies of the variables provided to them. Okay, I would like to explore this in a bit more detail because it's very important for us to understand when and where our variables live and how we can access them. Here is an example that illustrates some of the aspects of Python's scoping. I have two integer variables x and y, and I define a function f that takes three input arguments x, y, and z. Z has a default value of 17 here. Then inside my function I print the values of x, y, and z. I then assign or reassign the value of 19 to the variable y. So that's a new value for my variable that I have already used here, right? And I print out again x, y, and z. Outside my function, I define an integer variable z with the value 3, and then I call this first print statement here, which just prints out x, y, and z to the console, and you can see the result here. Clearly, x, y, and z have the values 1, 2, and 3 in this example. Now we come to the next line. I call f with input arguments x and y. Because z is not provided, I will use the default value, and therefore Python will print out 1, 2, and 17 to the console. Then we overwrite the value of y with 19, and we print out 1, 19, 17 as expected. Now, as this function completes, I end up with this print statement here, and I will print out 1, 2, 3. And you notice that even though we have modified the variable y inside my function, it still has the same value as we printed out here, namely 2. Okay, so this modification of the value of y has not really affected the value of y outside my function. And that really means that this variable y here is local to my function. It's a local variable in my function, and any changes I do perform on this variable will not affect the value of this outside variable y. Let's discuss another aspect. I have here a function f that simply prints out a value of a variable x. It then assigns the value 3 to this variable x and prints out x again. Before that functions, but outside that function, I assign the value 17 to x, and then I call it. Now this leads to a so-called unbound local error that we have seen before indeed. Python tells us that the local variable x is referenced before assignment. Now why is this the case? Well, I define x to have the value 17 outside my function, but it's only outside the function. So this value x is not available inside my function. I'm only defining it here, right? So I have tried to use the value of x before defining it on the next line. So that's a local variable that I try to access before defining it. Now what is a bit strange behavior if you come from different programming languages is that the following example will actually work. If you remove this assignment of the value 3 to x inside your function and you just have something like this. You define f to print out x, you define x outside your function, and then you call it. This is actually a valid program that runs without any problems. Now this behavior is caused by the fact that some variables live inside functions, some live outside of them. and this is exactly called the scope of a variable. Each programming language has its own rules of scoping, and in Python the most important rules are as follows. There are global variables that are those that belong to no function. They exist from their first assignment until the end of the program, or when they are deleted manually. And then there are local variables which belong to some function. They are created with the first assignment inside a function. And this can be through the header of the function. So if you have some optional values that you want to assign, that would also count as a local variable. And these local variables exist until the function execution is completed, or when they are manually deleted. It's very important that local variables lose their value between two calls to the same function. Finally, there are so-called static variables that exist in some programming languages, for example in C. These variables belong to a function and cannot be accessed outside of a function, and they maintain their value between different function calls. Static variables do not exist in Python, but it's possible to simulate a very similar behavior if one wanted to. In Python, global variables are generally not accessible in functions. Okay. But there are some exceptions. If you have a variable that is never assigned a value, like the variable x in this example here, it will indeed be accessible inside the function. So you see here, we have defined the variable x to have value 17 outside our function, and there is no assignment to x inside our function. Therefore, Python allows us to actually access the global variable x inside here. And there are variables that are explicitly declared to be global using the global statement. So if you go back to this previous example, which caused an unbound local error, we can make it work by adding the global keyword to that function. So now this variable x here, although it's being assigned inside the function, will be available to this print statement, and the value it will take is the one that we have defined outside our function. Now it turns out that using this global keyword is usually not a good idea, and the reason is that it kind of invalidates the idea of black box behavior of functions. If you have by accident used a global variable or a variable name outside your function that coincides with the name of a global variable inside that function, you might see some very unexpected behavior without knowing it. Okay, so that's why we generally recommend not using global variables. So I just show you that this global keyword exists, but the general recommendation is to always avoid using it. I'd now like to discuss a concept called lambda functions. They exist in functional programming languages, but also in MATLAB and JavaScript, for example. The main idea of a lambda function is to be a function that doesn't need a name. Okay, so it's kind of like an anonymous function. In Python, they are very simple. They only compute something and return it immediately. Okay? And they should not contain more than one line of code. And they also don't need the return keyword, because they simply compute a value, and this value that is being computed is automatically returned. The way we define lambda functions in Python is, not surprisingly, using the lambda keyword. So here's the definition of a lambda function called S that takes two input parameters x and y. We have a colon here, and we simply compute the sum of x and y. So let's try this out in Spyder. Okay, when I call S with input parameters 2 and 3, I get 5 as the output, and that's exactly the value that we compute inside our lambda function definition here, which is exactly the term that follows the colon. Okay. The name of this function, in a sense, is S. So you can in fact define functions and assign them to variables in Python. This variable S now refers to a function that can take two input parameters. We call lambda functions exactly in the same way as we call standard functions. The implied name is the one that we used on the left-hand side of this lambda assignment here. So this function can now be called by the name s. And this example is completely equivalent to defining a function s using the def keyword and returning the sum of x and y using the return keyword. But you see, these are 2 lines of code, and if we don't really need the return keyword, or we don't have any branches here, then why not define it in a simple manner using a lambda function? It's even possible to write functions that create other functions. Okay, so this is a concept that you might want to think about it for a little bit longer. Here's an example that hopefully clarifies this a bit. So I have a standard function using the def keyword called mkinc, which you can read as make increment, which takes one input parameter called inc. And this function does the following. It creates a lambda function that takes one input parameter x and then returns x plus the increment. Okay. So this here defines a function, and this function is then returned with the return keyword. So I can call my mkinc function with the input parameter 1, and what it will do is it will return me a function which I call I1 that I can use to increment input arguments by 1. And I can create another function, an incrementer by 7, and assign it to the variable I7. Now I have a lambda function available that I can use to increment values by 7. Okay, so you can see this here. I can call I1, which is now a function, with the input parameter 17, and it will return the value of 18 because it's an incrementer by 1. And I can call I7 with the input parameter 17, and this will return 24 because I7 is a function that increments its input parameters by 7. Now this example shows that functions in Python are just a somewhat special type of data. And we have seen this before when we didn't call a function itself, so when we omitted the brackets, but instead we printed some of the data belonging to that function. In this case it was the function max1. Recall that we could print the docstring of a function, in this case max1, using this syntax here. Okay. And we can also give a function as an input argument to another function. I have not discussed this in detail, but you can do the following here. Instead of printing the docstring like so, you can use the help function that is available in the PyDoc module in order to print out the docstring in a nicely formatted way. All this shows is that we have defined the function max1. We can call it to compute the maximum of 2 comparable input arguments, but we can also do other things with it. For example, we can access its docstring. In other words, if you refer to a function without the brackets, it is an object. So f itself is an object. Whereas if you want to actually call the function and execute its body, you need to include these brackets. Here is an example that makes this clearer in the so-called Boolean context. If you have defined a function in Python, its Boolean interpretation is true. Here is a function f that takes an input argument and prints out a string. It doesn't really matter what it's doing. All that matters in this example is that I can call bool of f. And this will now not actually execute what is inside the function. It will just return true if this function has been defined. Okay. So you can check if a function exists by calling bool of f. Now, if you want to actually call this function, you need to include the brackets. And that's shown here. I have a function again called f that takes no input arguments, and all it does is it returns false. Now I have this following if-else statement here. I ask if f, and if this is true, I will print out f evaluates to true, f evaluates to false. Now from what we have discussed here, this is merely checking whether f exists, and f exists, therefore this will print out f evaluates to true. While if I'm doing something something like this here, I have if f brackets, and this will now actually execute this function. So it will go here, it will return false, come back here, and then because the returned value is false, I will jump to the else block. Right? So this will evaluate to false and therefore print out f brackets evaluates to false. So very important that calling a functions without the brackets simply checks for the existence of a function, whereas if you call it with the brackets, you will indeed evaluate it and use the returned value in the Boolean context. What else can be done? We are not going to discuss this in more details here, but functions can indeed be defined inside other functions. Okay, so you can have a function f that defines another function g inside of it, just being properly indented. This can be sometimes useful for organizational issues or uses, but we will not make use of this here. And also you can have functions that call themselves, and there will be an example in the lab exercises on that. But generally, we will not deal with recursive functions in this course. A few words about code structures. We can use functions to structure our code into independent blocks, and you will find that this makes it much easier for you to write and read computer code. It's very important to make good use of functions, and for the lab classes and tests, it will actually be required to present your solutions in terms of functions. Just to give you an example how a code should be structured. Let's say we are tasked with writing two functions, let's say my function 1 and my function 2, for computing the sum and product of two input arguments. Okay, very simple example. How would I go about writing this code? Our program should roughly look as follows. We define a function, my function 1, that takes two input arguments a and b. Then, as usual, we have a docstring that explains what our function does, and inside the body of our function we are computing the sum of the input arguments as required, and then we return the sum. And likewise we have this function called my function 2 that computes the product of the two input parameters and returns it. Okay, this is our computer code. Now we want to test whether these functions actually behave as expected, and we will do this using another function called main. Let's say my main function is as follows. I just define some arbitrary values a and b here, 5 and 3, and I will print out the returned value of my function ab. Now I know that my function 1 computes the sum of the input parameters, so my function 1 of a and b should return 8. And my function 2 of a and b should return the product, which is 15 in this case. So let's copy and paste this to Spyder so we see it in action. Of course, if I execute this code, I will basically see nothing on the console because I'm just defining functions, but I'm not really calling them. So in order to see any of my tests being performed, I need to call my main program. And as you can see, I get the two print outputs here, 8 and 15. That's exactly the values that I expected. So I'm happy, and I trust that the two functions that I have implemented here behave as I intended to. Here's a very common mistake that I would like to address, and I hope you will avoid right from the start. It is a common mistake to include input commands inside functions, even though the function's arguments already provide the required variables. For example, here is a function called myFun, which takes an input parameter x. But then somewhere inside this function, we are asking for an input from the user to reassign it to the variable x. This doesn't make any sense, because if I want to call this function myFun, I need to call it with a value provided for x. Therefore, the value for x is already available here, and I do not need any input commands further on in my function, right? So please make sure that you avoid using the input command inside functions. It's really not needed. If you really want the user to input a parameter for the function you want to call it with, then you should do this inside the main function. Okay, so I have here still my main function, myFun, which does some computation with x. And if I really want the user to enter the testing value x, then I can do this inside my main function. I highly recommend avoiding the use of input at all. If you have a function myFun that does some computation and you want to test it within your main function, I would recommend using predefined fixed values for the input parameter. Okay, so you see I'm testing myFun here with the input parameter 17, and I have somehow worked out that the returned value should be 317. Also, I'm testing myFun with the input parameter 0, and I know from somewhere that this should return 28, and I'm just comparing what I expect to compute with what my function actually computes for a few selected meaningful inputs. Now, why is this much better than using input? When you write your myFun function, every time you do a change, you can rerun this main function for testing, and you can double check if it's still performing as expected. Right? So this is much quicker than having to type in some values on the keyboard every time you want to test your function for another iteration. Right? So make sure that you test your functions excessively and using meaningful inputs, but I really recommend using fixed inputs like so. Do not ask the user, or yourself in this case, to enter values to test with over and over again as you run your program. Now, this last example of a main function is an example of what is called unit testing. Unit testing is the concept that the developer, in this case you, of a function also provides a collection of tests. Right? So whenever you write a function, let's say myFun, it is good practice to also provide a number of tests, so that whenever you happen to change your original function, you can double check quickly if it's still performing as you expected. This will allow you to keep track of computer codes much easier if you are within a larger software project, for example. So this brings me to the end of today's lecture. I hope you enjoyed it. Just a quick recap as usual. We have learned about functions. So functions can be thought of as black boxes. So every function takes some kind of input, does computation, and then it returns a value. Right? So that's how we think of a function. The definition of a function is as follows. We use the def keyword in Python, then we give a good name to our function, in this case myFun name. The same rules as for variables apply. You cannot use spaces, for example, in function names. You have to use underscores. You cannot have a function starting with an integer, let's say. It should be a letter, but of course you can have integers or numbers inside your function name. And as long as it's not at the beginning of the function name, right? Then we have brackets, and we have the input arguments, let's say x, y, z, in this case 3 input parameters, followed by a colon, and then we have an indented block, typically starting with a docstring, which describes what this function does, okay, and what input parameters it expects. Then we have some form of computation, and at the end we typically want to return a value that we have computed using the return keyword. Right? So that's the basic way of defining a function. We have also discussed so-called default values for input parameters. So if I want to call my function using only 2 parameters, I can say, well, in this case, use the value of 13 for the variable z. And we have also seen how one can insist that named variables are also called always with a name by using the star operator here. We have spent quite some time discussing the difference between local and global variables, and that global variables are actually accessible inside a function if there is no assignment to that variable. So just make sure that you read this very carefully, the difference between local versus global variables. And most importantly, please refer to this last bit of the lecture again, where I highlighted this very common mistake. I just want you to avoid it right away. It does not make sense to get some input parameter, let's say x, from the definition of a function and then have an input command inside that function. So the general rule is no input commands inside functions. And also I explained you a good way of working with functions using unit testing. So if you write a function, also provide a testing function with it. In this case, it was called main, which calls your function with different sensible choices for the input parameters and just double checks that you get the expected outputs for each scenario.